Hello, my name is Alve Rahman. I'm a graduate student in Texas A&M University, Kingsville, and I'm proud to be able to present in front of such a panel. Today, I want to propose an online battery data analytics pipeline using big data tools for electric vehicles. This research was supported by Sungshil University, Seoul, Republic of Korea, and was conducted in Texas A&M University, Kingsville, Texas, USA, in collaboration with my colleagues and my advisors as shown in the slide. This here presents a brief overview of our proposed paper, which contains the introduction explaining our problem statement, the related works conducted earlier in this line of work, and the inspirations taken towards conducting this research. We then explain our proposed pipeline in detail while mentioning the listed methods. Moving on to our results, we describe our feature engineering techniques, our ML model's performance on new data, and we will validate our obtained results in detail. Lastly, we come to the conclusions regarding our estimation and future adaptations. In an effort to introduce our problem statement, we mention the following facts in the slide, while acknowledging the growing use of lithium ion technology in vehicles, aeroplanes, and whatnot. Battery powered technologies allow us to reduce our carbon footprint and dream for a greener yet sustainable future. In order to achieve this, a plethora of research is focused towards the reliability and safety concerns surrounding lithium ion technology. Before 2021, we received countless incidents regarding battery malfunctioning, generation of hazardous fires, and causing major panic attacks among social groups. The battery state of health and the battery remaining useful life are two key research areas that focus on operating conditions of the battery, the maximum load capacity, and the charging or discharging thresholds of the battery system. As seen in the slide over here, a vehicle caught fire due to electrical failures of the battery system. This graph gives us a better idea on how we should approach our research in battery SOH and battery remaining useful life. As shown over here, we can see that the failure threshold of lithium ion batteries is 88% of their state of health. This inspires us to further investigate the estimation capabilities of machine learning model in these use cases, also to propose a pipeline which is cloud deployable and easy to use using open source tools. As shown in the cloud-based battery health monitoring and analytics figure, conventional battery systems have been transforming into cyber physical battery systems. Battery health monitoring and analytics platforms like Voltaic and BetterY are commercially available but not open source. In recent years, the reputed company Bosch announced a cloud based software that enables companies to remotely access, manage, and monitor battery status to identify wear and tear in EV batteries. As shown in the slide, recent studies have thoroughly focused on the usefulness of lithium ion batteries and the capability to estimate the remaining useful life as well as their state of health. Recent studies have shown that the charging protocols typically go through constant current mode followed by a constant voltage mode. It is widely known that the duration of the constant current captures the polarization phenomena in lithium ion batteries. The constant voltage mode duration is thus crucial to eliminate the polarization effect caused during constant current mode, allowing for the anode to recover and thus fully charge the battery. Therefore, as the battery ages, the constant current charge time decreases, while with aging, the constant current charge time increases. As shown in the slide, we identify raw battery data, which include date and time, charging cycle, current supplied, voltage across the battery, charge capacity, and discharge capacity to convert them into 22 different and impactful features as shown over here. The charging data was supplied by Sandia National Labs and had a chemistry of lithium NMC. Once the features are generated, once these features are generated, we introduce these features to a machine learning model while assisting its performance and capabilities. Moving on to our proposed ML based battery pipeline using big data tools, we acknowledge 5 steps that are essential for successful battery data analytics deployment. Firstly, we introduce data ingestion through the form of Apache Kafka and Zookeeper. Data processing is proposed to be handled by machine learning techniques and algorithms while also keeping in mind distributed processing techniques like Apache Spark. In the case of big data storage, we need something robust and secure to store millions of streams of data in a distributed database. Apache Cassandra and MongoDB perform vital role in establishing a data storage pipeline for big data battery analytics. Visualization tools like db3.js, Grafana Labs, and many more provide real-time data visualizations while assisting and being compatible with big data storage tools. Lastly, we propose the use of the Docker container, which facilitates the use of such big data tools all under one cloud deployment. A simpler version of the previously described pipeline is proposed in this paper I'm presenting today. We work on 3 distinctive features of big data analytics pipelines like data ingestion, data processing, and data visualization. In order to set up our data ingestion pipeline, we introduce the use of Kafka Stream and Apache Kafka Topic. Apache Kafka Stream and Apache Topic can communicate easily through message interfaces and can exchange data with temporary storages like the KSQL database. Once our raw data of 6 columns are stored in the KSQL database, we pass that data inside our data preprocessing pipeline. The pipeline includes a cloud deployed Jupyter notebook, which has pre installed dependencies for machine learning and feature engineering, as shown in the slide. Lastly, our estimated state of health and our actual state of health are visualized and compared in detail to identify the performance of the machine learning model we used for the estimation. Lastly, as shown in the figure, the whole pipeline was deployed in a Docker container with simple curl commands. We can access each pipeline and initiate the transfer of data as well as the preprocessing and finally visualizing it. The following slide properly depicts the Docker containerization we talked about in previous slides, as well as the capability and the storage facilities inside Apache Kafka while explaining the connection between the Kafka topic and the KSQL DB. Developers can easily use a Docker Compose YAML file to Specify multi-container applications, which make this an easy to use big data tool to integrate such dependencies required to propose a big data analytics pipeline. Data from the Kafka topic is stored inside the KSQL DB as shown in the previous slides. Our experimental setup utilizes an M1 Pro SoC from Apple. It has 10 CPU cores and 14 GPU cores for allowing efficient use of the Docker container and to run all the big data dependencies that we are showing in this figure. Our data is batched in 1,000 rows each, for making it 82 batches of raw data to be exported inside the Apache Kafka. The M1 Pro SoC efficiently performs feature engineering in 18.5 seconds per batch of data. We choose the Docker and Kafka dependencies in such a way to fit the M1 SoC's ARM-based architecture. The Unix-based system allows curl commands to run directly from its terminal and to be able to configure any big data pipeline at will. We also use the M1 Pro SoC to train our models, among which the GPR, the Deep Neural Network Ensemble, and the Random Forest models are trained to find the best possible estimation. In order to validate our choice of algorithm, we mainly train three machine learning models on our specific dataset. The Gaussian process regressor, designed using an RBF kernel, the deep neural network ensemble, which has a learning rate of 0.001, three densely connected layers, and a mixture of activation functions, ReLU and leaky ReLU. The best performing model, as shown in table 2, the random forest model performs admirably, as shown by its accurate matrix in the table 2. And we designed the random forest model using an n estimators of 1500, a max depth of 18, and minimum number of leaves 6. Once we derived that the random forest was the best suited algorithm for our use case, we deployed it by saving it in an HDF5 format. Once saved, we deploy the machine learning model on our newly collected test data to be validated on its performance. As seen before and even in this slide, the random forest model can accurately estimate battery state of health till the point of point eight, till the point 85% battery state of health. As shown before, the failure threshold of battery SOH was 88%, and thus, as shown in the figure, our model accurately depicts the battery SOH till 88%. In fact, it would be safe to say that the machine learning model accurately depicts battery SOH till the 350th charging cycle. As seen in the figure, after the 400th cycle, there is a change in the estimations, although small. We believe that there are much algorithmic improvements we could achieve in this proposal. In conclusion, we explore an online machine learning based battery data analytics pipeline using open source big data tools in order to create an open source platform for everyone to use. The proposed nearly real time ML platform will enable new levels of experiments and analysis as we go through technology advancements like quantum computing and quantum annealing based optimization techniques. The feasibility of the proposed pipeline for an EV battery system is validated by thorough experiments of the machine learning model and through multiple experiments of the data ingestion and processing pipeline. Further research includes the use of a distributed and parallel processing system like Apache Spark adding more prognosis and state estimation algorithms, and lastly, to, to include big data based visualization tools like D3.js, Graphene Labs, and etc. Finally, the security based implementations of Apache Kafka, Apache Cassandra, and Apache Spark could be analyzed more in detail from a cybersecurity perspective. This research was supported by the Ministry of Science, ICT, Korea under the High Potential Individuals Global Training Program 2021. The project was supervised by the Institute of for Information and Communications Technology, Planning and Evaluation, IITP. This marks the ending of my presentation for our proposed paper in the conference ICPE ECCE Asia 2023. We have a question and answer segment for 4 minutes, which starts now.